In this video, we're going to make a model that lets us divide the gain we calculated in our last video into a few separate effects, and then we'll latch onto those effects to define design specifications that we can apply to all amplifiers. We calculated a relationship between small signal VC, our amplifier's output, and Vin in our last video, and I've copied the small signal model we used to do that calculation and our final result onto this slide. This gain depends on a source impedance driving the amplifier, because RS appears in the term, and it also depends on what load impedance the amplifier is driving, because an RL appears in this term. And that seems a bit weird. We'd like to be able to design amplifiers that work for any combination of sources and loads. So having dependence on the source and the load in our amplifier gain expression feels a little bit off. However, one thing that stands out is there's a voltage divider in this expression between our source resistance and R pi parallel RB. R pi parallel RB is entirely internal to our amplifier. That's a part of our amplifier, while the source resistance is not. So maybe that suggests a way to separate out our amplifier behavior from the world around it. We can get closer to that by expanding this parallel combination of resistors a little bit. So here I've just taken RO parallel RC as one resistor and RL as another, and made the parallel combination explicit. And then we can factor out a term from that expression to find a second voltage divider equation embedded in this equation. So this first voltage divider equation is between the load and some internal property of the amplifier, RO parallel RC, and the second one is the one we were looking at earlier, between R pi parallel RB and the source. That means we can, and then the remainder looks like a voltage gain. It's dimensionless GM times some resistance, RO parallel RC. So it looks like our gain is broken up into three parts: a voltage gain, an output term, like an output divider, and an input term, some sort of input divider. So this formatting suggests a model for the amplifier that would capture the same gain, where we represent the input by some impedance that divides with the source, and we represent the output as a Thevenin equivalent. Dependent voltage source that captures the amplifier's gain, and then a resistance that gets into a divider with the load. These three parts of our generic amplifier model have names. The first resistor is called the input resistance, or Rin. The second part is the voltage gain, or AV, and the third part is the output resistance, or Rout, where AV here represents the thing you multiply by Vin to determine the dependent voltage source's value. Notice that I'm using small signal notation for each of these, which is a reminder that this generic amplifier model is for calculating small signal gains. It's not telling us anything about the large signal behavior of the circuit, just about how a small change at one part translates to a small change in another. With these three terms defined, we can say that the output voltage of any amplifier is equal to an input loading term, which is a divider between Rin and RS, a gain term for the voltage gain, and an output loading term, which is divider between the load resistance RL and the output resistance. This generic amplifier model is a bit of an extension of models that we've already seen. It clearly has some properties in common with small signal models because we made it out of a small signal expression. And it also seems to be informed by Thevenin modeling because the output looks like a Thevenin equivalent. However, this model has two ports, which means that we've extended our previous models. Up till now we've only looked at circuits that had one port. Because of that, it's worth formalizing how we calculate Rin, Rout, and AV, because doing so will allow us to think about both what conditions are important when you have a second port, and how we might measure this in a lab. So we formally define Rin as the inverse of the change in input current to the amplifier with respect to the input voltage. However, this derivative has to be taken under a lot of conditions. The first is just that we want our circuit operating at its bias point. When we find Rin. And that's because Rin is a small signal quantity that depends on the bias point. Second, we want to make sure that we have the output resistor loaded with a load resistor that represents a standard load for this amplifier. Though our model doesn't suggest that RL can affect Rin, Rout, or AV, this model cuts a few corners that we'll talk about at the end of the slide, which makes having the proper RL here really important for measuring Rin accurately. Finally, we want Rs to be 0 when we're taking this measurement, so that we're only measuring Rin, right, and not some other series resistance that's added to it. That's a nice ideal, but in practice, we're probably going to add some series Rs to use as a sense resistor because measuring voltages is easier than measuring currents. So it's fine to have a little bit of Rs that you just subtract off of your Rin, or to think of the input as a voltage divider. Rout is similar to Rin. We define the inverse of Rout as the change in the total signal Iout with respect to small signal variations in Vout. And as with Rin, there are a wealth of conditions on this definition. We have to be at the bias point. We need to have a correct source resistance, something that's typical for the amplifier. And we'd like RL to be infinity so that we're just measuring Rout and don't see RL in parallel with it. We have one additional constraint when we're measuring Rout, which is that we don't want our input voltage gain to interfere with our measurement. Because if this voltage source AV times Vin is moving around, then we don't know the voltage across Rout at any given time. So we make sure the input is small signal grounded. Note, this doesn't mean we can hook a wire from our input to ground, because that would mess up our bias point, right? That would be a total single signal grounding. We usually accomplish this small signal grounding just by making sure that Vin is set to 0, so that we're not generating any signal. Finally, voltage gain is defined as the amount of fluctuation in Vout when Vin varies a small amount. This measurement needs to be taken at the bias point, and we need Rs to be 0, so there's no input voltage division, and RL to be infinity, so there's no output voltage division, in order to measure AV effectively. So these are a great set of parameters that will describe our amplifiers really well. However, they look pretty different from a standard 2-port network, which I've included at the bottom of the slide for comparison. Now, we're not going to do any math with this in this class, but I do want you to look at the two for the rest of this slide to make one point. This is called a Z-parameter network, and it's only one representation that can describe 2 ports, but I'm not going to go too far down that rabbit hole. The only thing I want to point out is this element, this Z12 element, because it's a major difference between our amplifier model and a standard 2-port. Right, because this Z12 allows port 2 of a standard 2-port model to exert some influence on port 1. While in our model, there's no equivalent. Nothing that happens at Vout voltage will change the Vin port. So that's an approximation. Almost every amplifier has some feedback from Vout back to Vin. And that approximation holds really well for some amplifiers and kind of poorly for others. But we can paper over omitting this kind of feedbacky Z12 element in our model by making sure that RL is appropriate for typical for an amplifier when we measure Rin, and Rs is typical for an amplifier when we measure Rout. Because that way the values for Rin and Rout that we get will be reflective of any secret feedback that's inside the amplifier during standard operation. So Our model presumes Z12 is 0, so we don't model any feedback to the input. That means we need to take very careful care with making sure that we measure with the proper RL and RS. So in summary, we can decouple amplifier behavior from sources and loads with the generic Thevenin amplifier model that consists of an input resistance Rin, an output resistance Rout, and a voltage gain AV. The generic amplifier model is a two-port small signal model, so we define some conditions to measure and analyze Rin, Rout, and AV, which are this set of derivatives, and we sort of capture and isolate the two-port behavior by carefully controlling our sources and our loads.